Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
So welcome to this Back to Basics track, and welcome to this particular talk in the Back to Basics track, Designing Classes, the first of two parts. So allow me for 10 seconds to introduce myself. My name is Klaus Iglberger. By the way, I'm perfectly happy if you stick to the first name. So I'm Klaus, and I'm actually a C++ trainer and consultant. And for that reason, of course, I get into contact with class design quite a lot. So I do dozens of training classes every year. And virtually in every single training class, I talk about classes in some way or another. And that is now the experience that I would like to put into these 2 hours. Yet you can imagine that class design is something that covers essentially days. I have at least 2 days of training material just for classes. So now, unfortunately, I had to pick 2-hour material for 2 hours only. I'm actually pretty happy that it is 2 hours. 1 hour would have been worse, but it is just 2 hours. Now, you come to this talk, of course, with a couple of expectations. And I believe that most of you would imagine that I primarily talk about class mechanics, language details, etc. I will do it a little different, though. I've decided to actually start with a little more general approach. I'll start with design guidelines. And I know this is a little more abstract, this is a little more vague, but I believe the outcoming guidelines, the things that I want you to remember, are far more important than any language-specific details. Now, they usually always apply. And interestingly, later, the implementation details will definitely also build on these guidelines. So I think it's the right approach to start with a couple of design guidelines. So this part 1 will first of all cover the challenge of class design, then the design guidelines that I was talking about for approximately 30 to 40 minutes. And then, probably what you expect most, we'll dive into implementation guidelines. That is what part 2, so the succeeding talk will cover in detail. All right, so that challenge of class design. There is indeed a reason why we talk about class design, and there is a reason why I actually chose this start, because there is usually a root source of problems when we develop software. Of course, it includes not just classes, but virtually anything. And actually, it's pretty simple. The root source of all problems is change. If you don't have to change anything in your code, you're fine. If it works, indeed, you're just fine. But as soon as you change something, things might not be so easy anymore. But change is indeed the root source, the driving force. And it's actually the truth in our industry. Software must be adapted to frequent changes. That's the expectation. This is indeed why software is called software in the first place. In comparison to hardware, it's easy to change. That is the expectation. However, from your own experience, you definitely know already that it's not so easy. Software is not always easy to change. Definitely not. Sometimes you get an issue, you estimate it's probably a 2-day issue, but after 2 weeks, you realize, no, it's not that simple. No, it's not that simple at all. And so what makes software, the change of software so hard? Why is some software so difficult to change? Dependencies. It all comes down to dependencies in some way or another. Of course, there is physical dependencies, there's logical dependencies, and of course, dependencies can also be necessary, and dependencies can be artificial. It's mostly these artificial dependencies that make our life so much harder, that make it so much harder to change things. And so ultimately, dependencies are what you want to deal with. So essentially, what you want to do is you want to make your things easier. So just this one quote of one famous person, there's many quotes about that. Dependency is indeed the key problem in software development at all scales. And so your task as a class designer or software designer in general, of course, is to design classes for easy change and also to design classes for easy extensions. Now, that will be the key notes, the key messages that I have for you. This is the pieces of information that you definitely have to use whenever you write a piece of software. It's not just classes, it's virtually anything. But things should be easy to change and extend. Else, you definitely do have a problem. Let's talk a little bit about design guidelines. What can I do to actually, what is the problems with easy change and easy extensions? Let's first talk about design for readability. And also this is a topic that you could fill with a lot of information, but I've now picked the one thing that I find absolutely important in order to have reliable classes, and that is names. So spend time to find good names for all entities. And of course, there's a couple of examples in the standard library, like array. This is how it is documented at CppReference. Now, you know array for sure. Of course, you know what n means, but somebody who is new to the language, is it immediately clear what this n represents? Is this a good name for some size value? And that is probably a better name. We probably should name this size. That would be much, much easier to understand, much more intuitive, and therefore just better or more readable. So I think size would be much clearer at this point. But of course, other containers are affected too, like vector. Std vector itself is a questionable name. Yeah, there is good reasons why vector is called vector. Somewhere in the past, this was a reasonable choice. But today, we actually don't know if it's a container or is it supposed to be a numerical vector. This is what currently bites the linear algebra proposal. Now they have to use different names because vector is already taken. So, well, in retrospect, we could have found a better name. Or inside vector, there is the empty function. So a vector has an empty function that you, of course, know to return a Boolean value. But if you just see that in code, again, what does it do? Is this an action or a query? Actually, it proves to be a query. It returns true or false. Yeah, is the vector empty or is it not? But a better name definitely would have been is empty. Well, of course, in retrospect, it's always easy to say that something was not good or well named. However, this is a big, big topic. And there's a great talk about that. In 2019, Kate Gregory has talked about naming in general. Naming is hard, let's do better. And of course, this is also not a talk that gives you all the answers. However, it definitely makes you think, because it is, after all, one of the most important pieces of developing software, finding good names. So indeed, spend time to find good names for all entities. And yes, naming is hard because it requires empathy. So I didn't say it's easy, but it's definitely very, very, very important. All right, but let's design for change and extension. And I have a toy problem. We're now dealing with shapes. And I know this is one of these situations where people usually just drop off because it's boring. Yes, I know the example is not particularly clever, not particularly inspired, but actually I discussed this with a couple of people, and as one of my fellow MOOC++ organizers said, I'm tired of this example, but I don't know any better one. And so I'm sticking with this because it's just simple. It's some example that we'll not deal with for a couple of minutes only. And I'm starting to design some kind of shape hierarchy. After all, this is what many, many people do. And this is what also in my training classes, we end up with in the beginning, a shape hierarchy. And I have a shape class in the very beginning that comes with a pure virtual draw function. So that draw function, of course, needs to be implemented in various kinds of shapes, like for instance, circles, squares. And please imagine that there's a few more. 2 is probably not enough. Now that could already work for some time, but from a design issue, this is actually already questionable. When I implement the draw function inside circle, when I put all the implementation details of drawing inside circle, and generally speaking, if you put all the implementation detail of some specific function inside a particular class, you create a dependency. And this draw function might now create a dependency to OpenGL, to VTK, 3DX, some big graphics library. Also, you can imagine that this makes it particularly hard to change things later. Now you want to switch from OpenGL to something more modern. You would have to change things, all of the code. You have to change something in all the deriving classes. And apparently there's only one possible implementation. So this approach is pretty limiting. Now, what can we do about it? Well, the naive approach is to just add another layer in the hierarchy. So let's do not implement this in circle, but add another layer to actually show these different implementations. OpenGL circle. That, of course, implements draw by means of OpenGL. Metal circle, 3DX circle, all kinds of circles that are implemented, that implement this draw function differently. And of course, yeah, we also do this on the square side, obviously. We create more and more deriving classes. Okay, perhaps for some time this works. Perhaps it makes some people happy. However, things change. That is to be expected. Things change, the code evolves. And let's say a couple of weeks later, we actually add another virtual function, a function called serialize. So that function is actually supposed to provide an implementation for putting circles, squares, and all the other shapes into a byte pattern. That byte pattern is supposed to be written to files or databases such that you can retrieve this information later and build exactly the same shape again. How do we implement the serialize function? Well, obviously, we don't want to do the same mistake as we started with the draw function, because also serialize has different potential implementations. So again, the most intuitive, naive approach is to add another layer in the inheritance hierarchy. An OpenGL little endian square and an OpenGL big endian square, which implements serialize in different forms. However, you do realize that you have to do the same thing with metal square again. And I don't even show it here. It's not particularly beautiful. The tree goes bigger and bigger. And suddenly we are adding duplication. We now implement the serialize function in two different places, probably pretty similarly. And you're starting to realize things are not easy to change or extend anymore. It actually starts to become a nuisance. And also other approaches like just directly implementing these in various forms here on the circle side is definitely not what you have in mind. Look at the names alone. Not particularly funny, no. So we have to expect change, but a naive approach, just building up an inheritance hierarchy, is probably not going to work well. So if you use inheritance naively to solve the problem, this very quickly leads to many derived classes. Very quickly, nobody really understands anymore what is happening. And look at the class names alone. Yeah, they're ridiculous. OpenGL little endian circle. There's also very deep inheritance hierarchies. Again, something that is hard to understand, definitely not simple, and definitely not easy to change or easy to extend. And we very quickly introduce duplication. So in other words, it's not fun to maintain anymore. And if it changes again, if you add a third function, and the slide is definitely out of space, there's nothing to add anymore. There's no room anymore. It's not fun indeed. So maintenance is heavily impeded, not fun. So the first guideline here, pretty please resist the urge to put everything into one class. And the secret ingredient here is to separate concerns. And if you use OO programming, yes, please use it properly. As we'll now see in a couple of slides, there is definitely right ways to use that technique. But generally, remember, design for easy change and design for easy extensions. That should be a driving factor, motivator for virtually everything that you design. So let's fix that. Let's actually do this better. And inheritance is indeed rarely the answer. Now, this is what the pragmatic programmer stated. What you should do instead is we should delegate to services. Has A trumps SA. And the right approach is, of course, going in the direction of design principles and design patterns. Now, let me give you 3 design principles that you should hold dear for whatever you're doing. First design principle is the so-called single responsibility principle. The second one, and don't worry, I'll explain them in a second. The second one is the open-close principle. And the third one for this presentation is the don't repeat yourself principle. 3 principles that basically always play a role, whatever you do. They're important. So the single responsibility principle. Commonly, this is explained as everything should do just one thing. Not the common wisdom of the community. However, this is probably also the reason why the single responsibility principle is criticized so often. That is something that you can virtually not use. It's super vague. What is one thing? What should I do? So how should it do things? What is single responsibility? The name is not particularly good. Unfortunately, the name is giving you the wrong idea. I tried to formulate it a little better. The single responsibility principle advises to separate concerns, to isolate and simplify change. Separation of concerns. That is something that you might have heard before, because that is just another name essentially for this SRP, separation of concerns. It is also known as high cohesion, low coupling, which is essentially the same idea. And the pragmatic programmers, for instance, called it orthogonality. So many names for the same idea, which is a clear indication that this is definitely something important, definitely something to apply. We'll just see how to use that in a bit. Then there is the open-close principle. That one advises to prefer design that simplifies the extension by types or operations. So it should always, at any point, be easy to extend my software. In the optimal case, by just adding a piece of code. I shouldn't have to modify anything. It should be possible by just adding code. And that explains the name of this principle. Open for extension, but closed for modification. So that is good design. And we'll see that this definitely is easily possible. And the last one, the DRY principle, the don't repeat yourself principle, advises to reduce duplication in order to simplify change. Because obviously, if you duplicate code, you might have to change things in many places. And that carries this enormous risk that you forget one place, that you introduce some kind of inconsistency or just bugs. And that, of course, is something that makes it so much harder to deal with the software. So duplication is definitely something that we should reduce as much as possible. Especially the complex things should be implemented exactly once. All right, and we'll also apply patterns. And there's a lot of design patterns available, but I'm reaching for the good old ones. For this presentation, I only need 2. And I'm taking from this book, Design Patterns, Elements of Reusable Object-Oriented Software. The classic on design patterns, published in 1994. And that is the so-called Gang of 4 book. It shows 23 of the most classic design patterns. Now, just that we're on the same page, a design pattern has a name, first and foremost, which tells you about some kind of intent. So if I now tell you we're going to use a strategy, then you should already have an idea what I'm doing, what I'm trying to achieve, how I want to move forward, and how I expect my code to evolve in the future. A design pattern basically always tries to reduce dependencies. It always helps you to structure your software a little better. And it definitely provides some sort of abstraction, some sort. It's not necessarily an inheritance hierarchy, as we'll see in a bit, but it definitely helps to structure software such that it can achieve the principles that I've just shown. And design patterns are definitely not something that fall from sky. They have to prove themselves, usually over a couple of years. They have to be used in many places before they actually can be called a pattern. All right, so let's fix the shape hierarchy that we've seen before by means of the so-called strategy design pattern. Now, I'm zooming in on circle, and we remember that circle had to implement some draw. Now, what we should not do is to apply inheritance directly. We should not have an OpenGL circle and a metal circle and what other kinds of circles we have. No, on the contrary, we should actually extract information. We should truly apply the single responsibility principle. By the way, last remark, of course, this circle represents all kinds of shapes. It could be square as well, it could be a triangle, it could be anything. So this is not a base class, this is a concrete class. We now use the single responsibility principle to extract the thing that we have found to change. So if draw truly changes, then it is a danger in the left-hand side class, a maintenance burden, potentially, perhaps not today, but in the future. This is what we extract. And a classic form of this extraction is to introduce another base class. In this example, it's simply called draw strategy. The draw strategy now introduces another draw function, which allows me to draw the circle. But most importantly, now I indeed delegate, because the circle owns the strategy. So this is the owning error. The circle may have a pointer, perhaps a unique pointer to a strategy, stores that one. And it is given that strategy by means of a constructor or a setter. This is what we call dependency injection. But most importantly, the thing that changes is extracted. That, as an aspect, is isolated such that it can now change things easily in one place, even test very easily. Because then I can implement this draw strategy in various forms. By means of OpenGL, Metal, 3DX, your favorite graphics library, I can use any kind of implementation. I can even provide something like a test strategy, mocking approach, which actually might work indeed pretty nicely if you don't really want to draw, but just want to see if it's generally working. So that idea allows you a lot of flexibility, and definitely change and also extension are suddenly easy, because by means of these derived classes, you can now extend the code trivially. If you want a new implementation, you just write a new class and you're done. You don't have to modify existing code anymore. So SRP and OCP in action, and it actually works pretty well. By the way, of course, we've also dealt with duplication pretty nicely. The dry principle is also covered here. Now in code, this might now look like something like that. The shape class is, as we've seen it in the very beginning. This defines or provides us with a pure virtual draw and serialize function. In other words, this needs to be implemented. But now the implementation of these is extracted. I may have this draw circle strategy. A draw circle strategy, again, provides a pure virtual draw function for circle. And now the circle uses that. The circle class, by means of the constructor, as said before, or by means of a setter also, is given a draw strategy. We do this by unique pointer. We pass by value in order to truly signal this circle will move that. This will take the ownership. So we move the strategy into our own data member. We now own that strategy. Whenever somebody calls draw, we just apply it. And so now the circle is completely independent of that drawing aspect. Doesn't need to know anymore. It's not depending. It's easy to change. It's easy to extend. That's a general thing that you find in design patterns or generally in all kinds of designs. That is kind of the secret spice. By the way, this is what I mentioned before, the dependency injection. I don't know my dependency anymore. I don't have to. I'm totally oblivious of how exactly I'm drawn. Big advantage. Now, of course, there is a square too. There's also draw square strategy. That's the disadvantage of this classic design pattern. I need one strategy implementation, one base class for every kind of shape. So the square is its own, but essentially it works in exactly the same way. I'm given a draw strategy in a constructor. I take ownership and now use that whenever somebody wants to draw me. All right. Now I have the liberty to implement any kind of drawing strategy. OpenGL circle strategy, OpenGL square strategy, everything's on the table. It's easy, and that's the point. And of course, in the main function, at some point, I will start to use them. And it's indeed easy to change things at any point. If you make a decision that the square now should be invisible because only the circles should be drawn, super simple. You just use a different draw strategy here. You do not have to change the existing code. After all, indeed, that is what it should be. So by means of the strategy design pattern, we have extracted the implementation details, isolated them. That's what SRP advises us to do. And so we have created the opportunity for easy change. We've also created the opportunity for easy extensions. And that's what inheritance hierarchies usually give you. And we have also reduced duplication quite a bit. Suddenly, we probably don't really have to think about this anymore. It's much, much easier to reason about this. And also, some very nice side effect, we have significantly limited the depth of the inheritance hierarchy. Definitely. So good things. And this altogether simplifies maintenance a lot. So again, design classes for easy change. Please, this is indeed the one thing that you have to keep in mind. Design classes for easy extension. It's kind of an obvious second thing. However, now what I did not tell you, exclamation mark, that you should always come up with any kind of additional base class for any implementation that you might have. That is not what I'm saying. What I'm saying is that if you find that you change that aspect, then you should take care of isolating it. But as long as it is working, okay, it may actually work. As long as you don't change it, it may be okay. So please don't guess. Don't guess what could happen in the future. Do not guess how the code evolves. But only if you know how this changes, make the according change. Now, make the according refactoring in order to enable easy change. But if you have no idea how things evolve, then just wait. Wait and learn from the next change, because that change is going to tell you how the system will evolve. And then you make the according refactoring that kind of change from now on will be easy. And that's how it usually should work. Keep it simple and easy to change. However, these guidelines make total sense, but you still complain. There's always somebody who complains. This is the nature of things, especially when we talk about design. And you complain that that's the style of the 90s, perhaps early 2000s. This is not modern C++ at all. I assume you do. Well, probably right. Probably you're absolutely correct. Today, we actually would favor different styles. The idea, however, is still exactly the same. So yes, today we favor a value semantic style. For instance, today we would not really go into direction of a base class anymore. For that purpose, we could actually use a std function. Std function represents some callable, and instead of getting a pointer to base, we can actually get a function object that tells us how to draw ourselves. It's so much easier. There's no pointers floating around. There is no real ownership anymore, no the ownership question. So we get a function object, we move that thing into our data member, and just use it as before. We call it whenever we need to draw ourselves. That is definitely nicer, easier to handle, easier to maintain, easier to understand. So better. But the idea is still the same. We extract the thing that changes. And of course, you could also argue that much nicer would be to do this by means of a template argument. So a circle at compile time is given as draw strategy and uses that whenever it needs to draw itself. Absolutely okay too. Yet again, it's still the same intent. We separate concerns, we extract the thing that changes from the class. It's still SRP, despite a different implementation. By the way, Andrea Alexandrescu called this policy-based design in 2001. It's still the basic strategy design pattern. It's exactly the same. So design classes for easy change and design classes for easy extensions. All right. I have a second example. I have a second example that uses the so-called template method design pattern. Now, let me give you a quick introduction to what this design pattern is about. The template method design pattern is actually not about C++ templates, not at all. It was named in 1994, perhaps even a little before that. At that time, C++ templates were not so prominently used everywhere, except for the STL probably. But the template method is just a function that is not a virtual function. This template method now defines some kind of primitive algorithm, some complete algorithm, an algorithm that may be a little longer, but has some steps, specific individual steps. And some of these steps might actually be very nicely configured. Some of these steps may actually, these steps make sense to be specialized in deriving classes. So these primitive operations, and of course there can be many, doesn't have to be two, they are virtual, pure virtual. They need to be implemented in deriving classes. Now, in what context does this make sense? Okay, let's take a look at this example. Our second toy problem, some persistence systems. I have a persistence interface. So this may be a base class for any kind of persistent system, a base class for databases, a base class for file systems. It's just something that I can use in order to write something to a persistent system, some backend. I can write, I can read. And of course, I have a couple of read and write functions. In this particular case, all of them virtual. Now, these virtual functions, actually in the future, perhaps not today, but in the future might pose a problem because things change. Software changes, it tends to change. And these virtual functions actually do not play well with change because they actually represent first the interface to callers. So somebody calls write in order to write something, and they also represent the interface for deriving classes. So I might change these functions for two reasons. Now, whenever one of these clients actually requires a change, I would have to change them. But of course, that would affect both the callers and the deriving classes. And so these virtual functions actually don't properly separate concerns. Change is harder. It might be even so hard that I cannot change things anymore. Also, this might, of course, potentially introduce a lot of duplication. All deriving classes might have to implement some pieces of this functionality again and again. Checking arguments, writing things to log files. There may indeed be a lot of duplication. So indeed, it is much, much harder to change. And I actually realized this in practice when I was still working in companies, that this kind of interface will not change. No, it will not change. People will rather work or introduce workarounds than change that because it's so difficult. So what can we do? And it is to separate concerns, to make things simpler. The idea is to not have virtual functions in the public interface. Write and read in this example are suddenly non-virtual, but now have virtual counterparts in the private section. So the first write function has a do-write counterpart, which is a private, pure virtual function. Of course, the second write has the according counterpart, and so do the two read functions. All of these functions suddenly have a virtual counterpart. By that, I have now separated concerns. Callers, of course, address the public interface. Derived classes, however, deal with the private interface only. And this gives me a surprising number of possibilities. Suddenly, I might actually have chances to change things. For instance, the first aspect may be duplicate code. That duplicate code now has a perfect home. These public non-virtual functions. So, okay, comment here. So there is indeed no virtual function in a public interface except for the virtual destructor. That's the exception. And this is why we call this in C++ the non-virtual interface idiom, a short NVI. It is indeed a thing we do in C++. This is not something I just made up. That is something that is indeed idiomatic, something that we use a lot for good reasons. So, for instance, I was saying that these public non-virtual functions provide the perfect opportunity to add all the code that else would be duplicated. For instance, in the first write function that I've shown, here the write, I could now write something to a log file first. Then I could change the arguments. If this blob has an empty name, I might never be able to retrieve it later from this persistent system. I can start time measurements. I can do many, many things before I do the actual thing and do write. I call the virtual function. That, of course, is the primary reason of being. So that is what this write function always does. It calls the virtual counterpart. But it can surround that with all the code that should not be duplicated and the code that must happen under all circumstances. Very nice. That is where you can change things easily. But of course, you can also change other things more easily. I don't suggest that it's super easy, but at least suddenly there is an opportunity. For instance, if you realize that this do-write function is actually not the only function, that it's probably better to split this function into two, I actually might be able to do that. I might be able to introduce another function, a virtual function, extend this template method design pattern from 1 to 2 virtual functions. So write, the upper right would now call these 2 functions. And calling code would not be affected. Calling code would be stable. Driving classes have to adapt, true, but perhaps in some scenario, this is actually not a problem indeed. Calling code usually is much more troublesome. So there is the opportunity to change code. There is the opportunity to do something. And so, again, okay, but by means of this non-virtual interface idiom, we have separated concerns and therefore simplified change, SRP again. We've enabled internal change that might not impact any caller. Perhaps that caller needs to recompile, okay, but still, the caller is happy because the caller doesn't have to change code. And we have potentially reduced duplication quite a lot. And we now know how we can keep duplication at a minimum. So, design classes for easy change and design classes for easy extensions. And so ultimately, this is what classes should look like. I know, colorful, playful, but the point is, of course, that you can put these things together virtually arbitrarily. Indeed, it is kind of easy to change things. It is kind of easy to add something new to that. I know, the mental image is just too tempting. I kind of like that. So classes should always be concise and focused on one purpose, SRP. So please separate concerns. You have several smaller classes. This usually is a better design. Then classes should be developed with extensibility in mind. There will be extensions. Of course, you want new stuff. It should be easy to add that. And also classes should be split into smaller pieces to favor use. Smaller functions, smaller classes, all of these definitely help to support this dry principle. All right. So then there's one thing that I want to do, rather quick one, because of course, testability is also something that we could talk for hours. Absolutely. So let's design for testability a little bit. And I've picked one aspect that I find particularly interesting, one aspect that actually is surprisingly dealt with differently in my experience. So let's say that we have a class called fixed vector. Now my contribution to containers. Fixed vector is now some kind of hybrid between an array and a standard vector. It uses static memory. That is this byte array down here. But it has maximum capacity. And note, first of all, the choice of names, capacity. It immediately gives you an idea what this fixed vector does. If that's the capacity, it's not the size, I can dynamically size that. So I can add elements by pushback or similar functions. And of course, I can remove them again. So I have a dynamic size up to that capacity. That, however, puts me in charge of creating objects in this buffer, but also destroying them. And that's what the purpose of this destroy function. And that destroy function is, of course, the function that is supposed to go through all the existing elements and destroy them, for instance, when the destructors run. Now, it's my responsibility to destroy the elements. But let's say that this destroy function is complicated enough to be tested. So you might not have seen the syntax before. Indeed, you can actually explicitly call a destructor. But because it's looking a little scary, you want to test that. So that's now the task. We want to test this function, and not just as part of some public function. We want to test it explicitly, but it's private. And so we cannot just call it, not easily test it. Well, in that situation, most people use the favorite search engine. They actually type in something, and very often they end up at Stack Overflow. And I actually found one very, very entertaining thread about how to test private members. So someone asks, what is the correct form to test private members of a class? And there's some answers, several answers, but of course there's the accepted answer. And that one says, one way to allow unit tests access to non-public members is via the friend construct. So we should add a friend. That's nice. Well, it's one way, but there's actually also a very funny answer in the notes above. Here, in C++, you can always do define private public. That is definitely something to think about. And then to cry out in horror. Of course, this is something that you should not do. That is horrific, which the next user, of course, complains about. A shame we can't downvote a comment. Pretty funny, though. So it is funny, but some people take this as serious advice. That's a little dangerous. So what should you do? What is your choices to test private members? So first, yes, of course, you can define private public, but that's absolutely not a solution. That's a hack. Now, if you use that seriously, stop using that. That's not a solution. That's basically the evidence that your design is flawed. Yes, of course, you could make the test a friend. Absolutely. It's always a choice, but not a particularly great one, because you've now created additional dependencies. You've coupled your test functional class, your test fixture into the production code. Well, perhaps sometimes, as a quick thing. Of course, you could make the member public. That makes me frown. But perhaps sometimes it may be a solution indeed. That depends. Usually, probably not. Yes, you could also derive the test from the tested class, but no, we do not want to derive from a class and prepare for this class to be derived from. That just feels wrong in most cases, except perhaps for the few cases where this is given anyway. But to design that way, specifically for that, no. Now, the right answer. The one answer is to separate concerns. So in this particular case, the separation of concerns can be simply achieved. So we can move the member into a private namespace that we use, that we know about. But so now since it's a namespace, since it's somewhere free, it's actually easy to test. It's almost trivial to test. Or we move it into another class. If you have additional data members, some state, then we could implement it as a separate service that is reused, but also testable. So separation of concerns. If indeed you fall into the situation that you need to test a private member, that is the thing that I would prefer. It feels the cleanest, and it's definitely supporting the idea. And you might have realized that this is exactly what the standard library does. Destroy in the standard library is one of these algorithms. It's to destroy. Vector, for instance, uses to destroy because Vector has exactly that idea. It needs to destroy the elements that it has created. Destroy can be easily tested, and these two work perfectly together. So resist the urge to put everything into classes. Okay, so resist the urge to put everything into one class in particular, and again, design classes to be testable. All right, which now brings us to the end of the design guidelines. Essentially, it's easy to summarize, design classes to be easy to change, to extend, and to be tested. So, and now we're at the point where we can start to talk a little bit about implementation guidelines. Class mechanics, code, that is probably what you like most. However, you will realize that many of the things that I now say is exactly the same message. Many of these implementation guidelines are based on the ideas that I've now already planted into your head. It's always the same. It always comes back to make things easy to change, make things easy to extend. Still, let's go through a couple of class implementation guidelines. And I'm starting with resource management, which is, of course, one of the most important things to talk about. Yet, of course, I will not talk about this in epic proportions. Let's say that we have a widget. And yes, this is, again, one of these examples of a name that doesn't really give you meaning. It's just some class. Some class that, first of all, as a repetition, has the six special member functions. The default constructor, the copy constructor, the copy assignment operator, the move constructor, the move assignment operator, and the destructor. That is now kind of the six that we will talk about a little bit. And also this class has data members. It has an integer I, which now for me is a representative of a fundamental type, meaning a type like, it could be a double two, could be a float two. It's just a representative. And I have a string, which is a representative of a class type or user-defined type. If this is all I have inside the class, if this is my two data members, then actually you may know that you don't need these special member functions. You can get rid of them. This class can work perfectly without these manual implementations. The compiler will implement these functions for us. This is why they're special member functions. And this is what we know as the rule of zero, or core guideline C20. If you can avoid defining default operations, do. That is simple. And again, if I don't write code, that code is kind of easy to change. I don't have to change anything. That's the simplest thing that can happen. So in that case, keep your class super simple. Sometimes this works, and hopefully it works as often as possible. But of course, sometimes it might not. And so I add a third data member, which is now a pointer. That's also a fundamental type, but I now see this as a representative of some kind of resource, some kind of responsibility. And of course, this is now a pointer that we have to think about. And the first question is, that's the question that C32 raises. So if a class has a raw pointer reference, consider whether it might be owning. If it's not an owning pointer, actually fine, we can stick to the rule of zero. Everything's nice. But if this is an owning pointer, life suddenly becomes more difficult. If a class has an owning pointer, define a destructor. That's probably a starting point. So we should definitely add a destructor, something that properly deletes the pointer. However, now we've added a destructor. Adding a destructor is now, well, unfortunate perhaps. It would be so much nicer to actually deal with all of these member functions explicitly. Because of this constructor, we would now have to deal with move. That is now gone. Then we would have to deal with copy, because with move written, the copy functions are gone. So things should be easy to change. The class itself should be simple as possible. And so core guideline R3 essentially says a raw pointer is non-owning. That means there's other ways to actually handle that pointer. We should not have a raw pointer, probably. If it is owning, we should make this obvious, readable. It should be easy to immediately pick that up. And so we probably should switch to a unique pointer, something that from code alone makes it easy to see that there is ownership involved. The code is suddenly self-documenting. So what I'm just reached now for is the most important resource guideline that we have. Manage resources automatically using resource handles and RAII, which of course is short for resource acquisition is initialization. And that is the one thing about resource management that you always should keep in mind. That is the one defining idiom in C++. Super important, perhaps the most important 4 letters in C++. So important that there's actually talks about that topic alone. So I definitely can recommend the 2019 talk by Arthur Dwyer. He talks 1 hour about RAI and the rule of 0, just about this aspect. Very good talk, really recommend it. And a couple of slides I also have the recommendation for this year's talk. However, going back to the code, that is what we should do. We should strive for the rule of 0. We should always strive to make things easy to handle. If you don't require to write any destructor or any other special member function, things are so much easier, including easy to change. However, as you might know, unique pointers cannot be copied. Unique pointers are unique ownership. Copying a unique pointer kind of does not express the right semantics, so it cannot be copied. This is why we now have to write the copy operations. You have to explicitly implement them in order to handle the copy behavior, if we want that. And I now assume we want. However, that means that the move operations are suddenly gone. The compiler does not implement these move operations for us anymore. So we have to write them. And we also would, for the sake of completeness, add a destructor. The nice thing is it's easy because I can default them. The unique pointer does all the work for us. These default implementations actually work perfectly fine for us. But the class suddenly is a little more complicated. Okay, sometimes this may be necessary. Sometimes we have to deal with that. But definitely it would be nicer if we could actually handle the rule of 0. But what we have right now is what we refer to as the rule of 5. Sometimes the rule of 0 just isn't an option. Sometimes you have to do something on our own. For instance, because we need a unique pointer. But then we do not just implement a few of these special members. We use all of them, always. So either 0 or 5. Now, of course, you could, again, complain, and you could argue that things are much simpler if you use a shared pointer. And you are correct. If we would use a shared pointer, actually all of this complexity would go away. I would not need any of these 5 special member functions. However, despite the fact that, of course, the class is now simpler, we have just fundamentally changed the semantics of the class. So shared pointers express shared ownership, unique pointers, unique ownership. And of course, this makes a difference. Now, do you have one resource for a lot of widgets, or do you have one resource per widget? So first and foremost, you should express the correct semantics, and then try to strive for the rule of 0. So yes, the rule of 0 is the best thing you can do in order to have a simple and a clean class, something that where you don't have to write code, and therefore change is simple, but sometimes it's just a rule of 5 as a backup solution. Still, again, strive for the rule of 0, but if it cannot be achieved, then follow the rule of 5. And design classes for easy change. The code itself should be easy. The code should be obvious what it is doing. Then it is easy to understand and change. And yes, the topic is so important that also this year we have a couple of talks for that. We have a talk by Inbar Levy, which I believe is on Thursday, I might be wrong, who talks about RAI and shared pointers in general. So that is something that you can watch, and also give another talk about the special member functions. Now, 1 hour just about these 5 or 6 special member functions. All right, but this brings me now to the end of part 1. All right. And I see that there is a couple of questions in the chat, which I'll now try to address because we do have a couple of minutes left. All right, so why are I read the first question from Vincent. Why are the virtual functions of the template method pattern private? Won't they be inaccessible from the subclass? Yes, absolutely correct. They will be inaccessible in the subclass. Yes, because the derived class cannot call the private functions of the base class. If they would be protected, you can call them. However, the subclass probably doesn't have to call them. Usually in a template method design pattern, the base class in this algorithm that you cannot change will call the virtual functions. It will call its own functions, which are of course accessible, but of course, due to virtual dispatch, we would choose the implementation in the derived class. So in a basic setup, you actually don't need to call the functions of the base class. However, some design patterns, for instance, decorator, might require you to do so. In that case, it is also perfectly okay to make them protected, but only as an exception. So these functions should be private, but they might be protected. Don't make them protected by default. You should be aware of this particular situation, I believe. Okay, I do hope this answers the question. Okay, so Ivan asks, small classes and lots of functions sound good in theory, but how do you advertise and document the classes and functions so that other developers can find and use them instead of re-implementing their own? That definitely is always a question, but it's a question of structure. Structure is the thing that makes your code work as a big thing. It's always the question about structure. How do I communicate there is an algorithm? Well, in a standard library, it's kind of obvious. We know them. But if you have similar things in your code, it should be known to everyone that there is a section for algorithms, things that should be reused. And this may be more algorithms than than a standard library provides. There's many more things that you could implement for yourself. So it's indeed a matter of structure. If things are just lying around somewhere, of course, they cannot be found. Of course, things will be implemented again and again. And of course, there's duplication. So essentially, it is your task, and of course, not just but the task of all your coworkers, to agree on some piece of information everywhere. So structure, agree on structure, make that work. And if you have no idea how the structure should work, then okay, keep things local, but still make them easy to change and testable. Okay, it's a hard question, but I believe this is exactly what you should strive for. And I don't say that the solution is easy. Designing software is a hard job indeed. Okay, Mihai asks, where can we find these core guidelines as outlined on slide 72? That is an excellent question. I kind of assumed that you've heard about them. If you've not, this is your opportunity to open your favorite browser, to go to your favorite search engine and to type in C++ core guidelines. Indeed, that is what you should do right now. The first hit, and I'm absolutely certain this will be the first hit, should bring you to the official collection of C++ core guidelines. This is a webpage that contains hundreds of reasonable, very good C++ guidelines. Most of them, I would say 95%, are implementation guidelines, but there's also a couple that definitely make sense on a higher scale. They're nicely structured, and they're continuously updated, extended, etc. Now, this is a living project of the C++ community. So just search for C++ core guidelines, and you should find them pretty much right away. Okay, and now I see that Vincent has already posted a link. Thank you for that. Alex asks, oh no, I answered that. Sorry, I didn't see that. Okay, Ryan asks, the gotcha of making private functions free functions to test them is that they often require access to object state. Now you need getters. Seems like the same problem as just make the method public. No, that is a misunderstanding. The function that you extract doesn't have to have exactly the same interface. No, the function should now take a couple of more arguments. That's all it needs. That's all you need. If you in the class, call a function, you just pass the state as arguments. That works wonderfully. You do not need to make anything public. You don't need to extend your getters, your public interface. Not necessary at all. Everything is still as protected, as private as necessary, as encapsulated as necessary. The function is adapted to actually work with you. It's not that you adapt to the function. No. That's not the point. You are in charge. The function is is doing what you want it to do. All right. So Philip asks, do these guidelines really support ultra low latency development? I'm not sure. Perhaps a few, but it's generally not the general guideline. And check them out. They're super useful. Okay, but now the time is out. So I hope I see you again in the second part, where we definitely take a look at many more implementation guidelines. So see you in half an hour.